Welcome back to our Centennial Speaker Series. Thank you for joining us for today's event featuring George Spiros. My name is Donna Rapiccioli, and I have the honor of serving as the Dean of the Gabelli School of Business. As many of you know, 2020 marks 100 years of purpose-driven business education at Fordham. Since our inception, we believed in the power of partnerships to inform and to lead change. So I'd very much like to thank the Gabelli Center for Global Security Analysis and our wonderful partners, the Museum of American Finance and the CFA Society, who are sponsoring today's conversation. The Centennial Series was designed to shine the light on important topics and trends. At the Gabelli School, one of our central teachings is in the area of economics, and at its core, economics is about making decisions. In his talk, George Spiro will give examples of mathematical paradoxes and psychological conundrums that have led to the advancements in economic science. Today's session will take place in a few parts. First, David Cowan, my friend and colleague, and the president and CEO of the Museum of American Finance, will introduce George. Then George will discuss his book, Risky Decisions: How Mathematical Paradoxes and Other Conundrums Have Shaped Economic Science. And we'll even challenge the audience with questions about how to make decisions and actually show people who believe themselves to be rational can also be led astray on occasion. Following discussion, David and I will facilitate audience questions. We ask that you use the Q&A section near the bottom of your Zoom screen to type in your questions, and our speaker will do his very best to answer as many as he can. I also want to let you know that participants in today's webinar will be entered into a raffle to win a free ebook of Risky Decisions. The winners will be notified by the end of the week. Before I turn it over to David to introduce George, I'd like to remind you that both the Gabelli School and the museum rely on your financial contributions to deliver on our missions. So that we ask that you consider making a financial donation to the Museum of American Finance or to the Gabelli School of Business Centennial Fund. If you look in the chat, you'll see the links there for you. Thank you for your consideration. Without further ado, I turn it over to David.
Thanks, Donna, and it's great to be back with you, our friends at Gabelli, as well as the CFA Society of New York. Now, our speaker today has an eclectic background and career. He's fluent in 4 languages. He was born in Vienna. He grew up in Switzerland, where he received a degree in mathematics from the ETH, whose famous alum include Albert Einstein. He went on from there to receive an MBA from Stanford and his PhD in mathematical economics from Hebrew University. And that PhD is all the more impressive when you find out that he did it part-time while working full-time as a consultant, a managerial consultant for McKinsey. He left that role to teach at Wharton and Hebrew University, but found his calling as a journalist for NZZ, which is known as the Swiss newspaper of record. While reporting as the Israel correspondent, he started a column on science and math. And speaking of writing, he's had a prolific writing career, over half a dozen books to his credit, several in progress, over 24 scholarly papers in math, finance, economics, insurance, and genetic algorithms. And as Donna just mentioned, his latest book will take a look at economic decision-making and rational behavior. So George, let's find out, are we rational?
Thank you for the kind introductions, Donna and David. I'm embarrassed about the nice things you said. I was supposed to be here last year, and of course that didn't turn out the way we planned. So I'm all the more happy to do it via Zoom today. So let me start sharing the screen. So I'll talk about decision-making, how mathematical paradoxes and other puzzles and conundrums have shaped economic science. How did economics develop? Well, it started in the early 18th century with a puzzle about the lottery, which I will show you in a few seconds. Then in the mid-20th century, mathematics became the underlying foundation for the modern theory of economics. And it talked about how ideal decision makers should behave. That's called normative economics. They should maximize and optimize. But as it turned out in the late 20th and 21st century, people don't behave like they should behave, like the mathematicians claim they should behave. That started a period of where psychology became the explanation for economics. So we'll start, how did economics develop? And we'll start in the early 18th century with a paradox. Let's play a game, coin flips. If you flip a coin, if it falls heads, you get $1. If it falls tails, it's flipped again and you get $2. If it falls tails again, you flip again. And if it now falls heads, you get $4. So the prize is doubled every time. The next time is $8, $16, $32. So if the coin falls tails 7 times and only on the 8th time it is heads, then the prize would be $128. How much would you pay to enter that game? Think about it for a few seconds. I'd love to see you all and see a show of hands. How much would you pay? But think about it. And now let's start analyzing this game. If the coin falls n times tails and heads on the n plus first flip, the prize is 2 to the power n dollars. The expected prize is the sum of the probabilities multiplied by the potential prizes. This is what you expect if you play the game many, many times. The expected prize would be this. So what is this? There's a probability that it falls heads on the first flip and then you get $1. There's a 25% probability that it falls tails on heads on the second flip, and then you would get $2. And there's 1/8 probability that it'll be 3 flips, and then you get $4, $8, and so on. So what is the expected prize? Well, half times 1 is half, 1/4 times 2 is half, 1/8 times 4 is half, and so on and so on. So the expected prize is actually infinity. It's unbelievable. This simple game has an expected prize of an infinite amount of dollars. So why is nobody willing to pay, let's say, $500 or $100? Most of you wouldn't pay more than just a couple of dollars to enter that game. Well, let's try to explain it. People always prefer more of a good than less of it. So for instance, 2 cookies are better than 1. 3 cookies are better than 2, and so on. But the more one has of a good, the less one wants an additional unit. So the 7th cookie adds very little pleasure. It adds a bit, but not much. And also that goes for money too. For a poor person, the first dollar may mean a meal. For a billionaire, it doesn't mean anything. The billionaire hardly notices an additional dollar. So Daniel Bernoulli thought about that problem in 1738, a Swiss mathematician, and he thought, how come if the expected prize is an infinite amount of dollars or thalers that they had then, why isn't anybody willing to pay a large amount to enter that game? And he wrote this very famous paper, and this is the picture of Daniel Bernoulli. And he said, he asked himself, what utility does an additional dollar give? Utility is not wealth. So we have wealth on the x-axis, and we have the utility of wealth on the y-axis. And we see he claims that the utility curve is shaped like this, which means for a poor person, $1 gives a lot of utility. For a rich person, another dollar gives very little additional utility. So he posited the logarithmic curve and says that approximates a person's utility of wealth. His colleague Gabriel Kramer said, well, let's take the square root curve that approximates a person's utility of wealth. So these are both utility and logarithmic. They're shaped that way. You see, bent downwards, which means every additional dollar gives you more utility, but the more dollars you have, the less additional utility does another dollar give you. And so now let's compute what's the expected utility of this game with the coin flips, not the expected prize, but the expected utility. What's expected utility? It's the sum of the probabilities multiplied by the square root of the potential prizes, if we take the square root curve as the utility curve. So what do we have now? We have 1/2 times the square root of 1, 1/4 times the square root of 2, and so on, 1/8 times the square root of 4, and so on. That's the expected utility. And what's that? That's 1/2 times 1, 1/4 times 1.41, and so on and so on. If we add that all the way to infinity, infinite amount of terms, what do we get? Previously, when we just added the prizes, we got infinity. But now we get a very regular number, 1.72. And 1.72 utility corresponds to $3. So that's a more reasonable amount that you would be willing to pay in order to enter that gamble, that game, that coin flip game. And that was Bernoulli's answer to the St. Petersburg puzzle. Expected utility, and now I want to explain a bit more how that goes over to economics. So we saw it was a gamble, and he explained why people aren't willing to pay an infinite amount to enter that gamble. Now let's see how that translates into real life decisions. Let's assume there's a half chance, 50% chance of having either $2,000 or $3,000. The A and D you'll see in the graph in a moment. The expected value of this chance is 1/2 times 2,000, 1/2 times 3,000, that's $2,500. Now let's look, this is the only complicated thing in the whole talk, but we'll go through it. So let's see, $2,000, $3,000, half is $2,500. But now let's look at the utility of $2,000. So we go up to the utility curve and we see the utility is 7.6. The utility of 3,000, we go up here, is 8. Now what's the expected utility? That's halfway between 7.6 and 7.8. That's where we have the point G. And now the next question is, this utility of 7.8 corresponds to how many dollars? So we go over to the point H on the utility curve, go down to see what wealth that is, and it is $2,440. So the expected value of this gamble or whatever was $2,500. The expected utility is $2,440. So that what that means is that people prefer a certain amount, a certain $2,440 to the half chance of getting either 2,000 or 3,000. And the $60 between 2,440 and 2,500 is the insurance premium. So let me summarize. A person who has a utility curve which is like this, that's the logarithmic utility curve, and is confronted with a half chance of getting 2,000 or 3,000, will prefer 2,440 for sure, rather than entering this gamble. Now, we know that most people have utility curves that curve downwards, like we just say. That's like what Bernoulli thought, and it's actually true. Most of us, except professional gamblers maybe, are risk averse. Well, we'll see some exception to that, but that's the basis of decision making in economics. I'll let you look at this graph for another few seconds, and we continue. So people are averse to risk, practically everybody. So now we jump 300 years, we come to the mid-20th century. Now mathematicians took over. I mean, Bernoulli was a mathematician, but now mathematicians took over economics, and they found the theories about how decision makers should behave in order to maximize their wealth or their profits. And these two people, John von Neumann and Oskar Morgenstern, they wrote a path-breaking book called Theory of Games and Economic Behavior. They wrote it in 1944, and it was a bestseller. Before John von Neumann and Morgenstern, expected utility was just Daniel Bernoulli's suggested solution to a mathematical puzzle, but they put utility theory on a sound footing, and it was called game theory. You may have heard game theory is a very, very important part of economics. So John von Neumann and Oskar Morgenstern, they posited that people are rational. And they said they have their famous theorem, given 4 axioms that I'll describe in a moment. A rational individual chooses one gamble over another if and only if the expected utility of one exceeds that of the other. So the axioms are completeness, transitivity, continuity, and independence of irrelevant alternatives. Let me show you the axioms of a rational person. The first one was completeness. It says, for all lotteries, you must be able to decide. You either prefer A to B or B to A. You can't say, I don't know, or you can be indifferent between the two, but you can't say, I don't know. Transitivity, if you prefer A to B and B to C, then you must also prefer A to C. Continuity is a bit of a technical thing. If A is better than B and B is better than C, then there's some probability that B can be made just as good as a weighted average of A and C. And now comes the clincher, independence of irrelevant alternatives. In mathematical notation, it goes like this. If you prefer A to B, and then there's some C and some probability P, then a combination of A and C will still be preferred to a combination of B and C. So if you prefer A to B, then even combining A and C will be better than B and C, which means basically C is irrelevant. No matter what C is, you'll still prefer a combination of A with C than a combination of B with C. So the theorem says if people subscribe to and act according to the 4 axioms, game theory should guide their behavior in risky situations. But now we have a paradox. I'm asking all of you listeners, do you have insurance, some insurance for your house, car, health, jewelry? And I don't see, but I suppose everybody is nodding. You have some insurance. Did you ever gamble? Now, you don't have to admit to it right here, but casino, sports, lottery, sweepstakes, everybody sometime gambles. But have you ever done both? You also have insurance to insure your house against, your content of the house against burglaries. And you also sometimes may go to a casino. So that's strange because people are willing to pay an insurance premium to avoid risk. They pay the insurance company, but they know that they pay a casino premium to assume risk. Whenever they go to a casino or buy a lottery ticket, you know that on average you're losing money because the casino makes a profit. So that's a paradox. Why do people pay to avoid risk and pay to assume risk? Does that mean game theory is not valid? Well, there's something called wobbly utility curves. The short answer is game theory is still valid. The long answer is as follows. Let's say somebody with $150,000 needs another $100,000 to buy a dream house. This person, totally irrational person, may want to gamble to attain that goal. So he or she will have a utility curve that between 150 and 250,000, the person is risk seeking. That means the dollar amount here, he or she is willing to pay for a gamble to the casino in order to hopefully win another $100,000. But below 150,000 and above 250,000, this person is risk averse. So that doesn't, even if you gamble and buy insurance at the same time, it seems a bit strange, but it doesn't invalidate game theory. And these are three people who published on this theory: Milton Friedman, Jimmy Savage, Harry Markowitz. Two of them got Nobel Prizes, not only for the insurance gambling paradox, but for many other things. But this was an important early step in all of their careers. So the question is, does math guide human behavior? We remember I mentioned 4 axioms. The theory is based on 4 axioms. If you subscribe to these axioms, which are all reasonable, then game theory is valid. The problem is, if you violate just one axiom, then game theory may not be valid. Let's say there's one problematic axiom. It's the independence of irrelevant alternatives. If one violates that, the independence of irrelevant alternatives axiom, then game theory does not guide your behavior and it doesn't describe your behavior. Let's show some examples of violating this axiom of irrelevant alternatives. It's very problematic. If you remember the US elections in 2000, George Bush won with 2,912,000. Al Gore lost by just 500 votes. But now there was a third candidate, Ralph Nader. He was completely irrelevant, would have never won the elections. He was the Green candidate. Now, if he hadn't run, most of Ralph Nader's voters would have voted for Al Gore. But the simple fact that he participated in this election changed the outcome. George Bush won because Ralph Nader ran. If Ralph Nader hadn't run, most probably Al Gore would have won. So we see decisions should be made independently of irrelevant alternatives, but aren't. Now, this is an example of collective decision-making, but there's a famous anecdote of somebody who made a decision himself. His name is Sidney Morgenbesser. He was a philosopher, a very famous philosopher at Columbia University. And he was once in a restaurant and the waiter came and said, for dessert, we have ice cream and fruit salad. So Morgenbesser said, okay, I'll take the ice cream. A few minutes later, the waiter comes back and says, we also have tiramisu. And then Morgenbesser said, okay, in that case, I'll have the fruit salad. Now, this is totally paradoxical. The fact that tiramisu was also available when tiramisu became available, Morgenbesser shouldn't have changed his preferences among ice cream and fruit salad. but he meant it as a joke to show how an irrelevant alternative like the tiramisu can get somebody to change his or her preference. And that's what happened in the elections in 2000. So somebody who also wanted to show that irrelevant alternatives make people change their minds and thus invalidate game theory was Maurice Allais, who got the Nobel Prize in 1988. And he was very proud of French science. So he meant to show that the American school was wrong. So he did it in the following way. Which situation do you prefer? Let's say the first case, you get $1 million for sure, or a 10% chance of getting 5 million, 89% chance of getting 1 million, 1% chance of getting nothing. Have a think for a moment. What would you prefer? Most people prefer A over B. They want $1 million for sure. They don't care about the 10% chance of getting 5 million. Now, another case. 11% chance of getting 1 million, 89% chance of getting nothing, or a 10% chance of getting 5 million, 90% chance of getting nothing. Think for a moment, what would you prefer, C or D? Most people prefer D over C. Why? Because the little difference between 89 chance of getting nothing and 90% chance of getting nothing is not important as compared to getting $1 million with an 11% chance, or $5 million with a 10% chance. So look at this again. Most people prefer A over B, and most people prefer D over C. Now, 1 million for sure can be split up in 11% chance of getting 1 million, 89% chance of getting 1 million. That's the same. A and A prime are the same. Everything else stays the same. And in the second gamble, 90% chance of getting nothing is the same as 89% chance of getting nothing, 1% chance of getting nothing. Now have a look at these 4 panels again. And let's look at the next panels. The first choice was 11% chance of getting 1 million, 89 of getting 1 million, which is also 89 of getting 1 million in B. So we can take these away. They're irrelevant alternatives because they appear both in A and in B. And now let's look at C and D. 89 chance of getting nothing and 89 chance of getting nothing are irrelevant alternatives. But as soon as this, what I crossed out, is added to A and to B, it's an irrelevant alternative. People prefer A double prime. And here, if we add 89% chance of getting nothing to both C and D, an irrelevant alternative, but people prefer D. And now we see both panels are the same, 11% of 1 million, 11% of 1 million, 10 of 5 million, 10 of 5 million, 1 of nothing, 1% chance of getting nothing. But nevertheless, if we add an irrelevant alternative, we prefer A. If we add another irrelevant alternative, people prefer D over C. And that is what Allais did. He invited many famous economists to a conference in Paris and showed them these questions, and many of them got it wrong. All these game theorists got it wrong. And anyway, that's how game theory all of a sudden became questionable. And there's also the same paradox, but in a different setting. It's called the Ellsberg paradox. I just mention it because it's too technical. Daniel Ellsberg, you may know who it is, a Harvard PhD, lieutenant in the Marine Corps, worked at the Rand Corporation, very famous for the Pentagon Paper scandal. He gave the Pentagon Papers to the Washington Post and New York Times. And anyway, before he did that at Harvard, he came up with a paradox to draw colored balls from an urn, and people, then he showed that people make the wrong decisions. They don't ignore irrelevant alternatives. Okay, that was game theory. So what next? Mathematics is the queen of the sciences, but man is the measure of all things. It's actually, we should see how people do behave, not how they should behave. And that's called positive economics. It's descriptive. This is prescriptive, how you should behave. This is descriptive. And this is where psychologists entered. The first one of the first ones was Herbert Simon, who got the Nobel Prize in Economics in 1978. That was, he was at Carnegie Mellon and taught psychology, economics, political science, computer science, everything. Anyway, he said, Homo economicus, that's sort of the a Latin word for the rational decision maker. Homo economicus. But he said Homo economicus is not an economic superman. Does the economic man, of course, man or woman, but anyway, Homo, economic man, does economic man have knowledge of what's around him? Does he have a well-organized system of preferences? Does she have skill in computation? Can they ignore irrelevant alternatives? Well, a normal person doesn't do all these things or cannot do all these things. Let's take an example, options trading. Options have been traded since the 1600s. People just, an option to buy in the next fall 2,000 pounds of wheat. So people take an option on that. And that has happened, has been going on since the early 1600s, just by gut feeling. But the correct price of a call option was by Merton, Scholes, and Fisher Black. That's the correct price of a call option, C. Now, nobody can compute that. A rational trader does not know how to do that. So Herbert Simon says, that's ridiculous that you use that one uses game theory to come up with, with equations that complicated that nobody could compute anyway. He didn't use these words, but I'm sort of putting words in his mouth. So game theory is not it. Herbert Simon says rational behavior must be replaced with behavior that is compatible with the limitations of a person in access to information, collection of data, processing of information, computational abilities, ability to deliberate all facts. So rational behavior is replaced with shortcuts. Let me give you an example. An annual growth of 10% is followed by growth of 40%. What's the growth factor over 2 years? The correct computation is 1.1 times 1.4 equals 1.54. But some people find it difficult to multiply, so they just add. You add 10% plus 40%, that's 50%. It's good enough. The error is quite small. So maybe we can use shortcuts. They give satisfactory solutions without much cost. You don't have to compute the multiplication. You can just add the numbers. So Simon says bounded rationality satisfies, don't optimize. Since you're boundedly rational, he didn't say irrational, he said bounded rational. Rational economic decision makers, they should satisfy, not to find the best optimum, which you can't, which is lots of computations, but just set a target, what you want. Once you reach it, stop. And The other thing, use rules of thumb, not higher mathematics. The term for rules of thumb is heuristics. So use of heuristics is rational. When you include in the total cost of decision-making, the search, the cost of data collecting, information processing, deliberation, there's a trade-off between search for the optimum and cost of deliberation. So you may as well use shortcuts and you get satisfactory results. And Simon says that's totally irrational. It's not irrational. It's rational to reduce your work and get a satisfactory answer, not the optimal answer. Now, what are the heuristics that Simon says one should use? They are rules of thumb, which are based on common sense and educated guesses, which are based on learning, experience, interaction with the environment, and feedback. So what heuristics do humans use? Use the information at hand, even if it's not very relevant. Round low probabilities down to 0, high probabilities to 100, believe evidence if it confirms your prejudice, exaggerate the importance of vivid over bland evidence, ignore new information, assign high probability to random events just because they happened yesterday, you remember them, rely on your own judgment, which is dangerous anyway, discern patterns in random data. These are technical, how do you call them, people on the stock market who do technical analysis. They double shoulders and so on. Suddenly they see patterns which don't even exist, take into account sunk costs, which you shouldn't, and fail to ignore irrelevant alternatives. So psychology is the new game. Kahneman got the Nobel Prize in Economics for having integrated insights from psychological research into economic science, especially concerning human judgment and decision-making under uncertainty. So let me give you some examples of how decisions are made. Think about this. Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. Which is more probable? Linda is a bank teller. Linda is a bank teller and is active in the feminist movement. Think about it for a second, which is more probable. Kahneman and Tversky, his co-author, they did an experiment and many people said Linda is a bank teller and is active in the feminist movement. But that's the wrong answer, because a bank teller, the bank tellers, they include the bank tellers who are active in the feminist movement. So more probable to be a bank tellers who are active in the feminist movements are a subset of bank tellers. So if anybody answered the bottom answer, he or she was wrong. It's more probable that Linda is a bank teller. Or let's see, in the flea market, you see a set of 8 perfect plates, you estimate the value of the $8. That's an experiment that Kahneman and Tversky did. The numbers may be off, but that's an experiment they did. Then the subject of the experiment, they got another set of 12 plates, 2 of which were cracked, and they estimated the set as $7.20. What they did, apparently, was they averaged out. Good plates are $1 on average, plates, some of which are cracked, are 60 cents on average, and that's how they got to $7.20 and $8. And that's wrong, because the 2 cracked plates should simply be ignored. But many people don't ignore them. They actually offer only $7.20 for the 12 plates, 10 good ones and 2 cracked ones. Framing is another thing that puts off people from the correct decision. Imagine an outbreak of a disease which is expected to kill 600 people. I mean, that sounds quaint today when we talk about the coronavirus, but when Tversky and Kahneman did this experiment, I guess that was a very major disease outbreak. Then they say, there's a vaccination A, 200 people will be saved. Vaccination B, 2/3 probability that nobody will be saved, 1/3 probability that 600 people will be saved. Which do you prefer? Or then they asked another question. Vaccination A prime, 400 people will die. B prime, 1/3 probability that nobody will die, and 2/3 probability that 600 people will die. Now, these two questions, vaccination A and B, are the same as vaccination A prime and B prime. 200 people will be saved, 400 people will die. That's the same thing. 2/3 nobody will be saved, 1/3 600 will be saved is the same as 1/3, etc., etc. Nevertheless, many people prefer A over B, and at the same time prefer B prime over A prime. Why? Because the question was framed. Here it says saved, 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 and here it says die, die, die. So the manner in which you frame a question may change your decisions. Vaccination of children leads to autism. Naive parents confused coincidence with evidence because they thought autism is brought about by vaccinations. Totally wrong. More deaths of lung cancer or traffic accidents. If you think about it, many of you will probably say traffic accidents. It's wrong. It's just traffic accidents are reported. Lung cancer isn't reported. Many more people die of lung cancer. Fear of flying, totally irrational. It's the safest way to travel. Nevertheless, people are afraid of flying because they hear about flight disasters. So we all have biases. The good thing about it is what Kahneman and Tversky found, that biases are systematic and can be predicted. We had, that was Linda, availability is you use whatever data is available, even if it's irrelevant. Adjustment from an anchor very quickly on a menu, wine menu, often you see a very expensive bottle at the top and then a still expensive bottle at the bottom, but it seems like a steal because the $600 bottle, you have that in your mind, then a $200 bottle seems like a really good deal. Sunk cost, one should never take into account sunk cost, but people do. Regression to the mean. So Kahneman and Tversky invented or developed prospect theory. Kahneman got the Nobel Prize. Tversky unfortunately died very young, 58 or 59, a few years before Kahneman got the Nobel Prize. They're both two Israeli psychologists, and I actually met both of them, so at the Hebrew University. So they say the prospect theory says there are, in decision making, there are two steps. One is first you edit the information you have, and then you evaluate. Editing is you combine information, segregate information, cancel things out, simplify, and see if something dominates everything else. That's sort of the text part of decision making. Evaluation, once you have all this information that you want to use, not necessarily that you should use according to game theory, but that people do use, then you start evaluating. And you evaluate using a value function. Bernoulli said we have to replace wealth with utility, and Kahneman and Tversky say we have to replace utility by a value function. And instead of probability, people use decision weights. Probability is a very mathematically precise data, but people don't use it. They use decision weights. Now, how is the value function? Let's remember that was the utility function of Bernoulli. But Kahneman and Tversky, they say we should use changes in wealth, not absolute wealth. This shouldn't be zero, but you're used to having $100,000, and now you start evaluating from the $100,000 on, up or down. For gains, you are concave. Your value function is concave. For losses, it is convex, which means it's shaped this way, which means risk-loving. Losses loom larger than gains, and that's the Kahneman and Tversky's new value function instead of utility function. So you're risk averse when you gain money, you're risk loving, you prefer to take a risk when you lose money, and this is steeper than this part. So that's the value function. Now the decision weights. Probabilities don't add to zero. Then some technical things. Small probabilities are overweighted. So altogether, if this is the probability, decision weights, according to the experiments that Kahneman and Tversky did, are shaped like this. And probably it's close to zero and close to 100%, it's undefined. I mean, at 98%, most of you would say, it's a sure thing. And 1.5%, many of you would say, that never happens. So prospect theory says first edit, then use value functions to translate dollar amounts, use decision weights to translate probabilities, and then make your decision. Compute and maximize the weighted value. So you use everything you have, all your biases, all your incomplete data, you just go with that. And that's what psychologists found out after. I mean, game theory is still a very important part of economics, but the last thing in economics is prospect theory. That's how people actually make decisions. And that's not irrational, but given the cost of making an optimal decision according to game theory, taking into account the costs, and maybe it's even impossible to make the correct decision because you don't have all the data, prospect theory describes best how people actually make decisions. So to summarize, we started with Bernoulli, the St. Petersburg gamble, which was utility theory. Then von Neumann Morgenstern, mathematics, it was game theory. Then Kahneman and Tversky, psychology, and we ended up with prospect theory. What's the outlook? Big data, that wasn't taken into account until now. Artificial intelligence, maybe people won't make decisions anymore. They'll just type it into their iPhone and decision comes out. I don't know what else may come. So the gist of my talk is, what do I want to tell? Be aware of your biases. Everybody has them. And as long as you're aware of them, you will make the best decisions under the circumstances. And I want to quote Attorney General Merrick Garland at the Senate confirmation hearing. Every human being has biases. That's part of what it means to be a human being. The point of examining the biases is to bring our conscious mind up to our unconscious mind. So it's not, you shouldn't be ashamed of your biases, but you should be aware that you have biases when you make decisions. And a plug for my book, that's the book that the whole talk was based on. You get a 30% discount, and you can order it at this, either at the Columbia University directly or at this URL, and be sure to add CUP30 at the checkout. Please also check out my new project on paradoxes, and I would be very grateful any corrections and comments. Thank you very much.
Thank you, George. That was great. I really learned so much. Thank you again. So we have a number of questions from the audience. The first one that I want to ask you is from Mark, and he says, you talked about people being more concerned about loss aversion. How do you explain what's going on in the market with some companies, for example, GameStop?
GameStop, as far as I know, and I didn't follow it completely, but it was more young people wanting to get back at the big traders. So I'm not sure that's rational, whether that enters the rationality debate at all. It was, as far as I know, it was some young people who were angry at Wall Street. So if anger and revenge enters, then we're outside of my domain. Sorry, not a very good answer.
No, a great answer. Thank you.
George, we've got a couple questions around the same theme from Jesse Cicernos and Max Rudolph, and they have to do with time. And Jesse says he's interested in your thoughts how time affects people's decisions. For example, a single person with a technical degree would spend more time investigating the risk of a decision versus a mother with 3 children who's very busy with the same technical degree. That's the first part. Max wants to talk about it in terms of similarities with time arbitrage. How do you avoid biases makes you more rational and able to use a longer time horizon for decision making? Do you agree with that, or is there a nuance? So two things with times, how it affects, and longer time frames.
Okay, I think both the working mother who doesn't have time to make a very profound decision and the engineer who may have more tools at his or her disposal, they'll do, given the costs for the engineer to gather more data, even the engineer won't make a totally optimal decision. Just both the working mother and the engineer will make the best decision they can make within 5 minutes. So maybe the engineer will analyze more data, but it'll also, the engineer has her own biases and makes the same mistakes, quotes, mistakes, because of taking shortcuts. And sometimes the shortcut gives just as satisfactory an answer as you analyze and collect data and compute probabilities, and then it's too late to make a decision. So I don't know if that answers the first question. The second question, time arbitrage, what was the question?
I see similarities with time arbitrage. Avoiding biases makes you more rational and able to use a longer time horizon for decision making. Do you agree, or is there a nuance I'm missing?
I don't know how to answer that. No, I'd rather, sorry, I can't give a good answer to that. I'd rather not speculate on that.
So George, I have a statement and then a question from one of our professors, Professor Shrish Chatterjee. He wants to thank you for a great exposition of psychology and behavioral economics, and as you compared it to rational decision making. He asks a few questions. He asks, what is mathematical psychology, and how is this new theory applied to understand financial markets?
Okay. Mathematical psychology is just psychology, and simply said, uses mathematical models, lots of statistics and mathematical models. To the second part of the question, a recent Nobel Prize, again, Richard Thaler, applied behavioral economics to financial markets. He even started a fund, behavioral finance, something. I don't know how successful it is, but understanding people's biases, you can make money because biases are predictable. And once you know how people make the incorrect decisions or short-term decisions, somebody who has a different view can actually make money. And that's what Richard Thaler, with his fund and with all his theories, he predicts that financial markets are driven herd behavior. We speak about herd immunity lately, but herd behavior, people just follow the leaders. If Warren Buffett says something, we'll also do it. So all these irrational, I shouldn't use the word irrational, but biased decisions, knowing that people make biased decisions can help you understand the market, understand what's going on in the market.
George, I've got first a comment from Will Snodgrass, who really thanks you for a great session, and then asks about our old friends. Are net present value and internal rate of return calculations a good way to compare and pick the best alternative?
One yes, one not. The internal rate of return, you may make, if you have $1 million and you can invest in one project where you get 20% return, but you can only invest $50,000, is not such a great investment. And to make just 5% on the full $1 million would give you a better net present value. And of course, net present value is what you should use, not the IRR, to make a correct decision.
So coming back to biases, can you comment on biases such as racism or gender bias and how you deal with them in decision making?
Okay, first of all, let me say the quote of Merrick Garland was not about decision making. It was about racial biases and prejudices. So the question, I don't think racial and gender biases enter or should not enter in financial decisions or economic decisions. So when I spoke of biases and prejudices, it's prejudice about regression to the mean, or prejudices about financial decisions, not about gender. I don't know what exactly the question was, but gender and racism should have no effect on financial decisions. But it's interesting that Garland talked about racial biases, and I took the quote as very indicative of what's happening in what Kahneman and Tversky actually found out.
And how about for our last one, Mark wants to know, what books did you read or what actions do you take to eliminate your own bias or do research on this topic?
I was trained as a mathematician. So in general, my decisions, not financial, any decisions are always, I try to do game theory. Von Neumann and Morgenstern are my first heroes. Kahneman and Tversky are my next heroes. So I try to decide what's mathematically better, which gets me in trouble sometimes with my wife because she makes intuitive decisions, and I get on her nerves with my always trying to optimize another 3%. But anyway, books, I read many papers for when writing the book, when writing my book. So I can't offhand say I have to look at what books I suggest, but it was mainly the papers of, the theory of games. That's the Bible. That's the Bible of the second part of my talk for all you mathematics people out there.
George, thank you. From Bernoulli to prospect theory. You taught us a lot today. It's been a pleasure on behalf of Fordham and the CFA Society of New York. Thank you so much, and good luck with your future books and work.
Thank you for having me. Thank you.